This is how I'd use the simulation in front of a class to explain the relationship between energy and voltage. I'd start with the show energy checkbox unticked, and then I'd probably introduce it by saying something like, here's our circuit simulation showing charges moving around a circuit. These moving charges are what we mean when we talk about an electric current. And then, depending on the class, I'd probably use a series of questions like this. We know that batteries eventually run down, so do they run out of charges? And the answer is no. What happens to the charges? They just go round and round the circuit. The confusion is that charge in English can mean fill up, as in charge your glasses at a wedding. So when we charge a battery, we are filling it up, but just not with electric charge. So what do we charge batteries with? What are they a store of, and what do they run out of? And the answer is energy. At a conceptual level, batteries run out of energy. At a concrete level, they run out of chemicals to react. Let's click the Show Energy checkbox. What do you think the red stuff represents? The red stuff represents energy. So what's the battery a store of? The battery is a store of energy. When we charge a battery, what are we filling it up with? We're filling it up with energy. If you think that electrons start from the battery rather than already being present in the wires, then it's easy to believe that eventually batteries must run out of electrons or electric charge. How is energy carried from the battery to the bulb? Well, the charges, or electric current, carry the energy. And what happens to the energy at the bulb? It spreads out into the surroundings. What feature of our simulation shows energy spreading out into the surroundings? It's the expanding red energy circle at the bulb. Which store ends up being filled up? It's the thermal store of the surroundings. There are two stories here. One, a practical story about how a filament lamp works. The other, a conceptual story about energy. And you should try not to combine the two. A filament lamp works because when it's connected in a circuit with a power supply, the filament gets so hot that it glows. And this is why filament lamps are so inefficient. They have to get hot to work. LEDs get hot too, but that's just a side effect of producing light. The energy story helps us create and connect ideas of voltage and power. The energy story helps us answer numerical questions about how bright the bulb would be or how long the battery would last. In our simulation, we show the charges themselves carrying energy from the battery to the bulb, and this isn't strictly correct, but it's very helpful if we imagine they do. In the same way, forces aren't really arrows, but it's very helpful to imagine that they are. If the speed of the charges tells us about the size of the current, what do you think the amount of red stuff around each charge tells us? It begins with V. It's the voltage or potential. The bigger the red circle around each charge, the higher the voltage at that point. Strictly, voltage or potential is a property of a location on the circuit, not a property of the charges themselves. But again, it's sometimes helpful to pretend that charges have a voltage. So you could talk about a 5-volt charge or a 0-volt charge. What happens to the amount of red stuff each charge has as it passes through the bulb? Well, it goes down. And what does that tell you about the amount of energy each charge has as it goes through the bulb? Well, that goes down too. And where does this energy go? It spreads out into the surroundings. So what happens to the potential or voltage as you go through the filament of the lamp? it decreases. And if the potential is 6 volts here, what's the potential here? Well, it must be 6 volts, 6 volts, 6 volts, 6 volts, 6 volts. And what about as you go through the filament? Well, it must go 6 volts, 5 volts, 4 volts, 3 volts in the middle, 2 volts, 1 volt, 0 volts. And what about the potential on this side? Well, the black dots have no red stuff, so it must be 0 volts, 0 volts, 0 volts, 0 volts, 0 volts, 0 volts. This idea of potential at a point is typically only introduced in advanced courses, but when we visualize it in our simulation, it becomes really useful because it's very obvious what we mean by the potential difference between 2 points.